Okay, are there any questions about any aspect of this course so far? All right. So far in the course we have seen, we're still in chapter 1 of the lecture notes of the book that I have put up on modal. And there are a host of models that are developed in that chapter. And you should study the ones that we haven't explicitly covered in the class. So my purpose so far is to develop one example of each kind of model, and then throughout the course, in assignments, you will get other models drawn from this chapter as we go through the theory behind each one of these algorithms. How does MATLAB solve it? So right now, we are learning how to do it, how to develop the model and how to solve it. Okay? And then we will answer the question, how does actually MATLAB get the solution? That will be the second part of this course. We know how to solve a system of linear equations. We know how to assemble it. We know how to recognize it. We know how to solve it. Inverse function, INV, or backslash operator, after you assemble the matrix AX equal to B. We know how to solve a system of nonlinear algebraic equations. We know how to assemble the model, and then we know how to write a function that can be used with fsolve. Okay? And we know how to solve a system of ordinary differential equations of the initial value type. The model that we saw is the molten metal in a crucible, but there are other models that lead to that class of models, initial value problems. So those are ODE 4.5, ODE 1.5S, etc. The theory behind it is very deep, and we will see a glimpse of it subsequently in chapters 2, 3, 4, etc. onwards. Okay, now, and we also know, even though we haven't explicitly covered that in the class, how to do function minimization. That is the current assignment for you. Okay, so how to construct an objective function and how to use fmin search. And if there are questions tomorrow in the tutorial, we will answer those questions. Okay, tutorial time is for you to be in the driver's seat and control the pace and ask questions. So the better you are prepared to ask questions, the more you will get out of that. Because I don't want to be kind of pumping one way when you're there sitting passively and watching. Okay, so I am scheduling this in the computer lab in chemical engineering. Unfortunately, I don't think the MATLAB still works there. It started working last night? Great, that's good. Okay, so we will have it in the computer lab, so that as I'm demonstrating it, I will ask you to do little exercises and observe and learn. Okay, as I said in the beginning of the course, one of my objectives is for you to feel comfortable enough to be able to learn more about MATLAB on your own, as and when you need it, when you're solving a particular type of problem. And today what I'm going to do is the next class of problems, which are called boundary value problems. Okay, ordinary differential equation and boundary value problems. So there is a function called BVP, boundary value problem, 4C, 5C, etc. And I will develop the model, try to understand the character of the problem, nature of the problem, and then we will show how to use it in MATLAB. How do I prepare it in MATLAB? Okay, so the problem is the following. This is from a heat transfer course. Okay, so you may have difficulty in conceptually understanding what is happening, but it is a device that all of us would have seen one time or the other, because these are what they call extended surface heat transfer devices, FINS. Okay, if you open up any computer on the top of a CPU, which generates a lot of heat, you will find surfaces like that, fins, that increase the heat transfer surface area, and so increases the heat transfer rate. If you open up in the front of a car, you will see a radiant cooler, and that has some fins too. And as you pass air through that, it is taking the heat away, the heat that is generated in the engine. Okay, so it is a very commonly used device, and what is happening physically is the following. We're taking a simple idealized example of that to be able to build the model and analyze it. And what is happening is you have a base plate, okay, onto which we are putting an extended surface. Okay, so that is the fin. What you see is the fin, an extended surface, and so it increases the heat transfer area. So the base temperature in here is going to be T0. That is, this entire solid block at the base of the fin is going to be at a temperature T0, which we assume to be known. Okay, so in the case of CPU heating up, we should be able to estimate how much of heat the CPU is putting out, and so what is its temperature at the top of the CPU is likely to be. From there, you want to conduct that heat away. So the mechanisms that are helping in taking the heat away from the base, that is from this surface, and transferring it this way along the length of the fin. The length of the fin direction, we call it as X. So heat is being conducted along the length of the fin, and then it is being convected. Convected meaning a fan is blowing air, so heat is being removed from this extended surface. This is the extended surface that we are talking about. Okay, from that extended surface, heat is being removed by convection mechanism. The details of these mechanisms you will see when you're doing a heat transfer course. Okay, but the concept of convection and convection, have you heard of it before? What is convection? That is electrical conductivity you're talking about. Okay, so if I take a wire and I apply a potential difference, okay, the electrons pass through it from one end to the other end, and that is the flow of current. Okay, so the current flows in the direction of a potential gradient, higher voltage to a lower voltage. You have seen that in physics, I'm sure. The same thing happens with heat. Okay, now here the electrons are not flowing, there is no current passage through that, but this is a solid material, so the molecules are not even moving. But ask the question, what is temperature? If I ask you the temperature, describe what you understand by temperature, what would you say?
Average kinetic energy.
Very good. It's a very precise definition. You have seen it in physical chemistry, I'm sure, right? Average kinetic energy of the molecules. So what happens is, when you pump energy into a metal, that energy goes to increase the vibrational and the rotational energies of the molecule. And that we call as representing the temperature. So the higher the temperature, the higher the energy is. Okay? So temperature is an averaged macroscopic quantity. The phenomena itself is occurring on a micro scale, okay? On the molecular scale. So whenever you set up a temperature gradient, we are saying the temperature, the heat is going to flow. As if the electrons are flowing in the case of electricity, the heat is flowing from the base of the fin to the tip of the fin. Okay? And then at this exposed surface is at a higher temperature than the room temperature. So again, the energy will be transferred by convection if the air is not moving. Okay? But the air molecules are free to move. The moment you heat them up, they become lighter compared to the neighboring air molecules, and gravity acts on it and it pulls up. So that is called a natural convection mechanism. Or if you blow a fan, you know at what rate you're blowing air, so that's called a forced convection mechanism. So there are models to capture how much of heat is being transferred by the convection mechanism. What we are going to do is assume that these models are given to us. What is the model for capturing rate of conduction heat transfer through a metal and the rate of convection heat transfer from the surface of the metal to the air? If you give me these two expressions, how do I build a model, and how do I examine what is the nature of the model? What are the conditions that I need to specify? Is it linear or nonlinear? What is the order of the differential equation? And what is the independent variable? What is the dependent variable? In this course, you should be able to answer all those questions. Those are the questions you will find in an exam. Okay? After building a model, you should be able to analyze those things. That will guide you in selecting the appropriate numerical tool from MATLAB or any other source that you use. Okay, any questions so far? I've attempted to describe what the physical description of the problem is. What is an extended surface? What are the mechanisms? And then we'll see the mathematical representation of these mechanisms. Any questions? Okay, so conductivity, the thermal conductivity is a property of solid materials. Okay, some are good conductors, some are poor conductors. In this case, we would want a good conductor because we would want to convey as much energy from the base of the fin to the tip of the fin, and then from the entire exposed surface that you see on the top and on the bottom, there are two surfaces. Okay? From those surfaces, you want to dissipate that energy to air to keep the base at a desirable temperature so that it doesn't melt out, for example. Okay? That's our goal. Now we want to develop a mathematical model. We want to translate all this physical description into a mathematical model. In order to do that, I'm going to have to ask you to accept mathematical representation of some of the mechanisms we talked about. The rationale for it you will see in a heat transfer course. So we talked about, for example, conduction. So I'm going to take a control volume. The control volume is what I've shown in the shaded area here that you see. Okay, so this is my control volume, and so it is going to be a rectangular slice. If I have to draw it as a thin slice, it's going to be something like this, with a thickness of delta x, because x is the direction in which the temperature gradient exists. Okay, so what is the dependent variable you are trying to formulate in this problem? Temperature variation along the fin. Okay, so T is the dependent variable, and it is a function of x, the independent variable. Okay, so this is dependent variable, and this is independent variable. And would this be yeah, sorry.
Do we need to concern ourselves with Lidl since the fan thins out?
That's a very good question. I'm very glad that you asked it. So the question you're asking in a sense is, in the y direction, will there be a variation in temperature, and should I be worried about it? Okay, it's an excellent question. In reality, if you have a tapered fin like that, you will have that. Okay, so you need to formulate this as a two-dimensional problem. So you have to identify T as a function of both x and y. The same principles that we are going to apply here is going to apply for developing a model like that. But that will result in a partial differential equation because you have two independent variables. Before we get to that complexity, we want to make a simplifying assumption. So what is the simplifying assumption that we are making?
Y is constant forever.
That the thickness of the fin is much smaller compared to the length of the fin. Okay, so if the thickness is very small, when I'm going up or down in the y direction, I'm not traversing a lot of distance. So I can assume reasonably that the temperature is uniform in the y direction. So that assumption will be a good assumption as long as the thickness is small compared to the length of the fin, and that is often the case in reality. These fins are extremely thin, but very long. Okay, the long because you want to have large surface area, exposed surface area. Okay, but if you decrease the thickness, we will see that it will affect the ability to conduct heat through that, because you also need a lot of surface area to conduct the heat. So there is an optimum weight. So this can be posed as an optimization problem. But that is the kind of question I would like you to think about, because it shows to me that you are understanding what the problem is, and you are critically analyzing what are the assumptions in the model. Is it valid? Okay, it's very important to go through that exercise. So we are assuming that there is no conduction in the y direction. We are neglecting any temperature gradient in the y direction. We are saying that there is significant temperature gradient in the x direction. Okay, so this is my control volume, which is a slice that I've taken from here. Okay, and this control volume has several surfaces. So from the left surface, I have heat coming into the control volume. Remember, what is my conservation of energy law? Rate of accumulation equals rate in minus rate out plus rate of generation. That's a concept that I'm going to apply in every case where I have energy balance, identifying a control volume. Okay, so the principle is rate of accumulation equals rate in minus rate out plus rate of generation, heat generation within the control volume. So that principle is applied on a control volume that I identify. In this case, my control volume is of thickness delta x in the x direction, but in the perpendicular direction, it is the thickness of the fin itself. Now, I'm allowing for the thickness of the fin to vary, and there is a reason why that is. Okay, and then I'm saying from the top and the bottom surface, the heat is being released to the surrounding air. Okay, and that is occurring at the rate of h times p times delta X. H is called a heat transfer coefficient. How to calculate that you will learn in a heat transfer course. Okay, but that is the expression that we are using where we are saying that I know what H is, and H has the units of watt per meter square degree C. So it basically says how fast am I losing energy? So many watts, joules per second, per unit area per degree C temperature difference between that hot surface and the surrounding. The surrounding is at a temperature of T infinity. The surrounding air is at a constant temperature of T infinity. Okay? So that is the mathematical expression for calculating how much of heat you're losing by convection to the surrounding. And P here is the perimeter. And it has the units of meter. And delta X, of course, is the thickness. And that also has the units of meter. So when I multiply this, what am I going to get? H times P times delta X. What will be the units? Watts per degree C, because the meter square will cancel out, because I'm multiplying H times an area. So P times delta X is the total exposed area that I've shown by shaded area here, in the top and in the bottom. So P is the perimeter, that is the length going around that control surface. So P would be this perimeter. And then I multiply it by delta X. That gives me the exposed surface area, okay, on the top and the bottom. Okay, and as we already talked about, on the left side I have heat coming in. I'm going to represent that as Q, the heat flux. What is the heat flux that is coming through the left? And this is evaluated at X. So I'm going to put a subscript X to indicate that is the heat flux coming on the left side of my control volume. And on the right hand side, I have Q at X plus delta X. That is the heat leaving the right hand side at X plus delta X, because that plane is at the position of X plus delta X. Okay. Now, how is that Q given? Q, again, is a convection mechanism. So you have another model, which you will see the rationale for it in the heat transfer course, but it is given by something called Fourier's law of heat convection. And it is very similar to what you will see in electricity. For example, here it simply says that the rate of heat transfer by convection mechanism is proportional to the temperature gradient, how steep the temperature gradient is. And the proportionality constant is your thermal conductivity. So K is a thermal conductivity. It is a property that is known. Okay, it's thermal conductivity. And it is known. Now, what is the units for Q? The units for Q would be the heat flux. How much of heat is, what is the rate of heat transfer per unit surface area? Okay, so this will have the units of watts per meter square, or joules per second per meter square. That is called the heat flux. Obviously, this should have the units of what? dt dx. Should have the units of degrees Celsius per meter, because delta T in the numerator is the temperature difference, has the units of degree C, denominator has the units of meter. So dt dx tells us how fast the temperature is decreasing in the x direction. So what should be the units for K? Yeah?
Wouldn't it be C over dm? Is it a differential length?
Yeah, but I'm talking about units.
Okay.
Okay, whether you have a differential between two temperatures, the units that is going to carry is simply degree C. Okay. Watts per
meter degree Celsius.
Very good. Did everybody get that? How many of you are totally lost at this stage? Put up your hand. Am I going slow then? That's the other question. I need to strike a balance. Okay. All right. So the K should have the units of watts per meter degree C. Okay. So that this equation, the Fourier's law of heat convection, is dimensionally consistent. You get the same units on both sides. Okay. So these are the elements that we need to borrow from a heat transfer course. How do I model the heat convection mechanism? How do I model the heat convection mechanism? Now I'm ready to put together the model by examining each one of these terms. Okay?
That DC over M, is that degrees Celsius or is that
Degrees Celsius, yeah, sorry. That is degrees Celsius per meter or degree Rankine per meter, degree Fahrenheit. It's a temperature difference. Okay? So, what can I do about the rate of accumulation? You need to ask me the question, is this fin operating under steady state or it is operating under transient state? What does that mean? Suppose I'm starting up my engine or I'm starting up my computer. Okay? So there is going to be a period when it warms up to an equilibrium temperature. So if you want to answer questions during that time period, including the question, how long does it take to reach the steady state, you need to include this term. So that will again make time as an independent variable. So the temperature will depend both on position and time. That will make it as a partial differential equation. So we're going to make a simplifying assumption that there is no accumulation, meaning it is operating under steady state, so that we can answer questions once this fin reaches a steady state. But we cannot answer any questions about how long it takes to reach that steady state. That's an assumption. Okay? And later on we will relax that assumption and see how to develop a model when you have transient effects as well. And that is also in chapter 1 of the book. On the right hand side, let's look at rate of generation. Is there any heat being generated inside the control volume? The control volume is this now. There is no mechanism for heat generation here. Where are the situations where you could have a mechanism? Suppose this were a catalyst pellet in a reactor. There is a reaction taking place. There is heat of reaction. And you are interested in predicting the temperature distribution in a catalyst pellet. You will have to worry about that. But in a fin, there is other one would be the resistive heating. When you're passing current, it generates heat. But in this case, there is no mechanism for generation of heat. So there is no generation. So our model simplifies to simply 0 equals rate in minus rate out. Now, what are the surfaces through which heat is coming into this control volume? Remember, this is my control volume. Through the left surface, heat is coming into that control volume. Through the right surface, heat is leaving the control volume. And through the top and bottom surfaces, also heat is leaving. So these should balance. Okay? I've already described how I'm going to calculate those heat rates in and out. So help me out. With this description, you should be able to write the model equation. So how would I write an expression for the rate of heat transfer in? It is a rate. So it should have the units of joules per second or watts. Okay? It should have the units of watts. So, but Q actually has the units of watts per meter square. Okay? So I can write this as Q multiplied by the area evaluated at X. The subscript X indicates that I'm evaluating this on the left surface, which is at a distance of X from the base of the fin. So X is the distance from the base of the fin, and at that distance, I know how to express Q. If I multiply that by the area, what area am I talking about? This area, the left side area. Okay, the left side area through which heat is coming in through convection, minus the rate out. You can fill that in, right? How would you write an expression for the rate out through the right surface? Q times A evaluated at X plus delta X. Now what area am I talking about? The right side area. Now are those two areas likely to be the same? Depends. If I have a fin that has a uniform thickness, then it will be the same. But if I have a fin that is tapered, then it will be different. The left hand side area will be different from the right hand side area. That is why I am putting it inside the parenthesis to say that A of X could be different from A at X plus delta X. Okay? What should be the units of these terms? Watts or joules per second, because these are rate expressions. right? And you can very easily check, because Q has the units of watts per meter square. We're multiplying it by A, which has the units of meter square. So the product should have the units of watts or joules per second. Are we done? No. We have one more surface, which is at the top and the bottom. And that is also minus, because it is heat leaving the control volume. Okay? And that is given by, as we already saw, HP times dx. Remember, what are the units for H? As I said, it is watts per meter square degree C. Okay? So if I take H and multiply by the area, what is the surface area? The exposed surface area. Now I'm talking about the top area and the bottom area. So I'm going around the top and the bottom. Okay? So H times P times delta X. That is the area. The perimeter is the length measured around that, and when I multiply that by delta X, I'm going to get the top and the bottom area. Okay? And multiply that by the temperature difference. And that temperature difference I'm going to write as T minus T infinity. That is my energy balance model for this fin. Any questions on any one of those terms?
Why did you put it like temperature?
Because, remember, each one of these terms should have the units of watts or joules per second. Okay? So the model for convection heat transfer says H is watts per meter square degree C. Okay? So first I multiplied by the area to get rid of the meter square. That says the amount of heat transfer by convection is larger if the area is larger. Okay? And then it says it is proportional to the temperature difference. And that temperature T is the temperature in this block. We are assuming that the temperature is the same in the vertical direction, the question that we raised. We are assuming that at the top and the bottom the temperature is the same. And then that temperature is different from the surrounding temperature in the air. So how fast heat is transferred depends on that temperature difference. Okay? So we write that as T minus T infinity. Any other questions on that?
Should that be two times?
Should there be two times because I have the top and the bottom? That depends on how I define P. P I define as the total perimeter going around. So I'm actually including even this exposed surface area on this side and the other side. Okay, so P is actually the total perimeter, not just the top length. If I define P as this length, then P times delta X gives me the top surface area. I need to put twice. Okay, but the way I have defined P is it's a total perimeter going around the fin at any particular position. Good. Any other questions? This is the most important step, because what we have done here is understood the physical description of the problem and translated into a mathematical language. Okay? From now on, it's a mathematical manipulation, preparing it for solving by MATLAB. That's the next step. Any questions? Question? You guys are discussing among yourselves. I'll bring up the questions, unless there is no stupid question. If you have a question, that others may have the same question. Okay, so it is important to bring it out and discuss it so that we can all make sure that we are understanding it. So if there are questions, please stop me and ask. What would be the next step? The next step is to take the limit of the control volume delta X going to 0. So it is just a mathematical step. All I'm going to do is divide this by delta X and divide this by delta X and take the limit of delta X going to 0 and ask the question, what happens to that equation? Okay. When I do that, the left hand side remains 0. The right hand side, I'm going to write this as minus QA at X plus delta X minus QA at X. I'm just reversing the direction, and minus the delta X here will cancel, so I'll get HP times T minus T infinity. So the delta X cancels out there because I'm dividing every term in the equation by delta X. Question?
I think you have an extra negative in your first comp term.
No, I deliberately reverse this sign. So this one has minus QA at x plus delta x. And then this has plus QA at x. So reverse it, put a minus sign there. Okay. Why did I do that? What is the physical meaning of the term in the brackets here? In the limit of delta x going to 0. Calculus. Limit process. This is how you define a derivative, right? How do you define the derivative of a function? Do you remember that from calculus?
Fn plus 1 minus Fn.
Divided by?
Divided by the change.
So, if you are lost, what we are talking about is if I have some function f of x versus x, the function is like this. I'm talking about what is the derivative of the function at that point. How do I calculate the derivative? How do I define that derivative? Okay, and that is simply take another point on that curve and then calculate what is the function difference. So we will write this as f at x plus delta x minus f at x divided by delta x. And in the limit of delta x going to 0, so this is delta x, the x-axis. And the y-axis is the difference between the function at x plus delta x minus the function at x. So as this point moves towards this point, you are taking the chord and making it tangent to the curve. And that is how we define. So in the limit of delta x going to 0, that is defined as df dx. That's a definition for the derivative. Okay? From your calculus. So that's what we're going to use to write the first term as minus d dx of q times a. Then the second term remains as it is, hp times t minus t infinity. Now it is a differential equation. Is it an ordinary differential equation or a partial differential equation? It's an ordinary differential equation because you have one variable that is a function of one independent position, x. Okay? Count the variables and identify the variables that we know. Okay? So let's do that. Do we know h? Yes, from the heat transfer course. Do we know the perimeter? Yes, from the design of the fin. Do we know the area? Yes, you should know the design of the fin from the design again. And what is q? Q is given by this. Okay, so we can substitute that q and replace that equation. Q is at this stage an unknown, but it is expressed in terms of temperature gradient from Fourier's law of convection. So we can use that using Fourier's law. We can write this equation as 0 equals. Now remember, q is given by minus k times dt dx. Why did we put minus there? That's a convention in the Fourier's law. To make sure that when dt dx is negative, that is the temperature is decreasing in the increasing direction of x. The temperature decreases and distance increases, the derivative is going to be negative. So the heat flux is positive always in the direction of decreasing temperature. And so the flux will have a positive sign. So just a sign convention that we are going to use. It's used typically. Okay. So when I substitute that, I already have a minus sign. I'm going to get another minus sign from q. So it's going to become d dx of k times a times dt dx minus hp times t minus t infinity. That is my model. That will be able to predict what will be the temperature variation along the fin, from the base of the fin to the tip of the fin. What is the order of the differential equation? It's second order. Okay, the highest derivative is second order. Yeah.
Do you know T initial?
A good question. What is T initial? T infinity is the room temperature, which we know.
So would it be 2?
Or is that the right question to ask? Initial temperature, it would be if I'm dealing with a transient problem where the fin is initially at room temperature and I bring the base to 200 degrees at time t equal to 0, and the temperature keeps on changing over a period of time. Okay, so in such a situation, what I will have is the following. Okay, so when you ask the question, what is the initial temperature? Suppose I have a fin that has uniform thickness. Okay, so this is x, and it is initially at T infinity, and the surrounding is also at T infinity. And then I will get a partial differential equation, as I said earlier, and this temperature will be a function of time and x. And then I can say initially, if this is T infinity and this is T0, initially the temperature is at 25 degrees, and the base at time t equal to 0 is brought to 200 degrees. How will the temperature profile evolve, both with distance x and with time? Then you will get a profile at very small time. The profile may be like this. And as you wait longer, the profile will become like this. Okay, so each one will be for a different time, T1, T2, T3, etc. And this will be T0. So when you're asking about the initial temperature, that is the context in which that question will make sense, right? That I'm dealing with an evolving problem in time. It is a transient problem. Here I'm looking at only the steady state problem. Okay, I have dropped this thing. So how would you rephrase that question? You are absolutely right in saying that I need additional information. What kind of information do I need? I have a second order equation. We've all done a differential equation course, right? When you are integrating, you are going to get two integration constants, right? So you need two conditions. And if both the conditions are given at the same x location, you will call that as an initial value problem. If they are given at two different locations, you will call a boundary value problem. So this is going to be a boundary value problem. So this is why it is important to recognize the order. The order is a second order equation, because the highest derivative that you have is d square t dx squared. Okay? So we need two conditions. Where would those two conditions be given? One is at the base of the fin, where I have already said that the temperature is at T0. This is the base of the fin. So this entire block is at a temperature of T0. So we can specify for that equation, these are called boundary conditions. Boundary conditions. We need two boundary conditions because it's a second order equation. One boundary condition is obvious, which says T at x equal to 0 is T0. T0 is a known value. The base of the fin, the engine is at 800 degrees, or the CPU is at 150 degrees, or whatever. That is known quantity. But we need additional condition. The additional condition, there are many options. Okay, physically there are many possibilities. One could be boundary condition 2, option A, is to say if I touch the tip of the fin, and if the tip of the fin is at room temperature, what does it mean? This is based on physical experiments. I need to determine what the boundary condition at the other end is, at the tip of the fin, when x is equal to L. So I should tell you that the length of the fin is L. Okay, this entire length is L. That is also given. So I'm asking you now, what is the condition at x equal to L, that is on this surface that is exposed? There are many possible conditions. One would be to say that that tip is also at room temperature. What does it mean? It simply means whatever the heat that has entered the base of the fin has all escaped through the top and the bottom surface. There is no more heat that is arriving at the tip. So the tip is at the room temperature. That's a physically possible condition. Okay, so the option A would be to say T at x equal to L is T infinity also. The other condition says that the tip area is so small in a tapered fin, for example, that there is no significant heat loss through the tip. And if there is no significant heat loss through the tip, that means the Q is 0. How can Q be equal to 0? Q is given by Q is given by K times dt dx. Okay, so if K is a material property, it depends on whether you're using copper or aluminum, it's a thermal conductivity of the material. That cannot be 0, so dt dx must be 0. Okay, in such a case, the tip could be very hot. The temperature is unknown. All you know is the amount of heat escaping through the tip of the fin is extremely small. Okay, so the case B would be that dt dx at x equal to L is 0. Sometimes you call this as insulated condition. Okay, so these are several scenarios that we can examine in order to solve this. Any questions? So we have two conditions and some variations on those two conditions, and we have a second order equation. Okay, and I think that's what you have in here, basically captured. So either this or dt dx equal to 0. The second boundary condition is one of them. So this is boundary condition 1 and this is boundary condition 2. One of those two as boundary condition 2. Now Q refers to the total amount of heat that is being taken from the base of the fin or exposed to the surface by convection that is being transferred. So if I know the temperature profile T of x, then I can calculate what the derivative is, evaluate at x equal to 0, multiplied by k. That will tell me how much of heat. This is what a design engineer is interested in. How much of heat can I dissipate through this fin? In order to answer that question, I need to know what is the temperature profile so that I can take its gradient at x equal to 0. Or I can plug this expression into this. Once again, knowing after solving T of x, I can calculate how much of heat is being released through the exposed surfaces by convection. What do you think they should be? They should match, because all the heat that is coming from the base of the fin, as evaluated from this, is going through the top and the bottom. Okay, so that these two should match. So that is the ultimate design objective, to be able to calculate what is this Q, how much of heat a single fin can dissipate. So what do we know about this at this stage? We know that we have a second order equation, ordinary differential equation. It's a boundary value problem. How do we know that? Simply by inspection. Here the two terms are. So it's a second order equation. Highest derivative is second order. And in this equation, we should know what the thermal conductivity is. We should know what the area is. We should know the heat transfer coefficient. We should know the perimeter. We should know the ambient temperature. What is the unknown? The unknown is only T. And it depends on only X. And there are two boundary conditions because it's a second order equation. Is it linear or non-linear? How do you answer that question? After having identified what is the unknown, you look for any products in the unknown or in the derivatives of the unknown. That will make it non-linear. Okay? So if K is a constant, the thermal conductivity is a constant, then it is a linear problem. Sometimes what happens is the thermal conductivity changes with temperature. That again has to come from experimental measurements. If that is given, then you will insert here K as a function of temperature. Then you will have temperature and the product of gradient of temperature. That will make it nonlinear. The same problem will become nonlinear if K is a function of temperature. But if K is a constant, it's a linear problem. If K is constant, then problem is linear. How about A? Can A change with distance? Obviously yes, if the fin is tapering. Okay? But I should tell you how it is tapering. Will that make it nonlinear? It will not. A could be a function of x, meaning at various x positions the cross-sectional area keeps changing, as in a tapered fin. Okay? But it will still remain a linear one. In a differential equation course, you might have seen this as a linear but variable coefficient, because the coefficient that is appearing in the differential equation is position dependent. Okay, and solution of that is extremely difficult by analytical means. You have to go to Bessel function or Fourier series and things like that. But MATLAB makes it the same, whether it is linear or nonlinear, constant coefficient or variable coefficient. The same few programs that you need to write will solve this problem. Okay? Any questions? So we're going to examine several cases. Okay, the first case is to say that I'm going to assume K is constant. I'm going to assume A is constant. By assuming A constant, what am I saying? I'm saying that the fin has a constant thickness. The thickness of the fin is constant everywhere. Okay, so this is distance, and this is x equal to 0, so the temperature is T0. At the final one, I'm going to take the case where T is equal to T infinity. So what I want to do is, I want to solve this differential equation to construct the temperature profile, something like this. Okay, this is T infinity, this is T0. My question is, what is the shape of the curve? What is the shape of that curve that will satisfy, when I plug that here, should satisfy that equation, and it should satisfy the boundary condition. At one end it is T0, at the other end it is T infinity. Okay, so how do I construct that curve such that it satisfies the differential equation in MATLAB? Okay, so I'm going to do this in non-dimensional form. Okay, so what that means is I'm going to redefine some variables such that this solution can be used for any fin that you design, as long as these conditions are met. Conditions of constant K and constant A. Any length fin, any thickness fin, etc. Okay, so I'm going to define theta as my dimensionless temperature. Remember, T has a dimension of degree C, but theta is going to be scaled such that theta will always go from 0 to 1. This is an arbitrary definition. So what I'm doing is, okay, I'm going to take T as my unknown. T is my unknown, and subtract T infinity, because T infinity is the reference temperature. Okay, and then divide it by T0 minus T infinity. What happens to this? If I define theta like this, what happens to theta at the base of the fin? At the base of the fin, what is T? T0. So what is theta? T0 minus T infinity divided by T0 minus T infinity. So theta will be 1. So the temperature profile will always start at 1. What is it at the tip of the fin?
0.
It's 0. It will always be 0. So I'm scaling my temperature profile between 0 and 1, if I can define that dimensionless group. I'm going to do the same thing for distance. I'm going to define a variable called psi, which is going to be defined as x over L. So L is the length of the fin. So if I plot this, here I'm plotting T versus x, here I'm plotting theta versus psi. Just to show you what the scaling does to the graph. So what would be psi at the base of the fin? X equal to 0. If x equal to 0, psi must be 0. Am I losing you guys? Or have you seen this dimensionalization before? No? There is really no magic to it. All we're doing is, in numerical methods of solving, it is always a good idea to scale it, so that numbers are nicely scaled between 0 and 1 in both the dependent variable and the independent variable. So in the dependent variable, this definition of theta allows you to vary theta between 0 and 1. In the independent variable, this definition, that psi equals x over L, will make it change between 0 and 1. When x equal to 0, you put x equal to 0, so psi will be 0. When x equal to L, at the other end of the tip, what does psi become? 1. Okay, so this is going to be 1. So you get a nice graph between 0 and 1 in the x-axis and 0 and 1 in the y-axis. That graph, once constructed, can be used for any length fin, whatever the base temperature is, whether it is 200 or 800. Once you have constructed the solution, you can apply the same solution to CPUs, where the base temperature may be 100 degrees, or car engine, where it may be 800 degrees. Because all you need to do is use that scaling definition to extract the result back in the dimensional domain. That is, what is the actual temperature, T, instead of theta. Okay, so that is the motivation for defining dimensionless groups. Now what I need to do is take this differential equation that I have and take the differential equation I have here and write it in this form in terms of the dimensionless variables. If I give you this task for 2 minutes, how many of you think you can do it? That is, show that this equation, written in terms of dimensional variable t as a function of x, can be rewritten using these definitions that I have in this form. Just an algebraic manipulation, but how do I do that? Okay. what I need to do is, are you guys comfortable doing that, or no? You're totally lost if I give you the task. Okay. So how would I do that? Let me move to the other page, and because I'm running out of page here. Okay. So the equation I'm going to assume k is constant, a is constant, right? So the first thing I'm going to do is take k and a outside the derivative because they are both constants. I can do that. Okay. So I'm going to write this as k times a times d square t dx square minus h times p t minus t infinity is equal to 0, with the boundary condition that t at x equal to 0 is t0 and t at x equal to L is t infinity. This is my problem in terms of the dimensional variables. And this is the same problem that you have on the other page, except I have taken k and a out because I have assumed k is constant and a is constant. Now I'm going to introduce these two definitions. I'm going to show you how to introduce those two definitions to write this in dimensionless form. So, do you agree that I can write the first term as ka d square over dx square t minus t infinity? Can I do that? T infinity is a constant. So when I take the derivative of t infinity, what happens? Second derivative, it is 0, right? So these two are basically the same if I write it as t minus t infinity. Okay? And minus hp times t minus t infinity equal to 0. The next step I'm going to do is I need to divide both the terms. That is, I can divide every term in an equation by a constant. Okay? So I'm going to divide this by t0 minus t infinity. And I'm going to divide this also by t0 minus t infinity because both are constants and I'm taking it inside the derivative. Okay? So the whole thing is operating inside the derivative. If any of those manipulations is not clear, please ask me to repeat. Okay? So what I have done is I have subtracted t infinity first because it is a constant. So if it is within the derivative, when I write it as d square t dx square minus d square t infinity dx square, which is going to be 0. Okay? So these two equations are the same. Then I divide every term by t0 minus t infinity. Now I recognize that what is this term? What are these two terms? Simply theta. That's all. There is no magic to it. So I can write this as k times a times d squared theta dx square minus hp times theta equal to 0. Okay. The next step is I need to transform. So I transform the dependent variable from dimensional temperature to dimensionless temperature theta. Now I need to transform the independent variable x. But what is x? X is defined as, from this equation, I can write x as equal to psi times L. Just taking across the L. Right? So that is the case. What is dx? If I take the derivative of that, what is dx? Remember, L is a constant, the total length of the fin. Right? So it's going to be L times d psi. So wherever you have dx, just replace it by L times d psi. Okay? Now if you have dx square, what do? L times d psi square, because square both sides. Okay? So this will become, the next step would be to make this as k times a times d squared theta dx square. So that's going to be written as L square times d psi square. The L square comes from the fact that dx square is the same as d psi square times L square. So that L square is in the denominator. Minus hp times theta equal to 0. So this then can be rearranged as d squared theta d psi square minus hp L square over k a times theta equal to 0. That is the process of putting in dimensionless form. Yeah.
How did you rearrange the d squared t of dx squared? I don't understand how you can just, yes sir.
So what did they do there? Okay. Let me just erase that and try to go through it one more time. Okay, so this is what I have. To begin with, I have, this is my starting point, right? So I have d squared dx squared t minus h3t minus t infinity. So the first argument I'm making is because t infinity is a constant, I can subtract it from t infinity and it will not change any equation. Why? Because when I take the operator d squared dx squared on t, that gives me the first term. When I take that on minus t infinity, since t infinity is constant, when I take this derivative, it's going to be 0. Okay? So I can subtract t infinity without changing the equation. Anything. The next step is I'm going to divide both times by a constant. And that constant is t0 minus t infinity, t0 minus t infinity. And that because it is a constant, I can divide it either inside or outside the derivative. Okay? And then I recognize that this entire term is theta. Okay? Any questions? Now, you need to help me with the boundary condition. I have transformed the differential equation from t x to theta psi. The reason I did that is theta now is going to scale between 0 and 1, psi is going to scale between 0 and 1. Okay, I won't have huge numbers in MATLAB when I go to MATLAB. So this you should be able to do in an exam, scaling so that you prepare it for MATLAB. What are the boundary conditions in terms of theta at psi equal to 0 and theta at psi equal to 1? When x equal to 0, what is psi? 0. And what is theta? When x equal to 0, t is equal to T0, the base temperature, as we saw. So T0 minus T infinity divided by T0 minus T infinity, which is 1. So this boundary condition is 1. When x equal to L, we saw T is equal to T infinity. So that means psi equal to 1, theta is equal to 0. So this is case A for the second boundary condition. What would be the case B? D theta d psi at psi equal to 1 will be equal to 0. That is the derivative condition, insulated temperature condition. So our task is to prepare this particular problem for solving in MATLAB. Any questions? I will, although this is a pretty poor handwriting, I will put a copy of this in Moodle so you don't have to write it down. Because I did write quite a bit today. So, we have now formulated the problem in terms of the dimensionless variables, which is here for the first case, okay, where this is the differential equation, theta is the dependent unknown, psi is the independent variable. The range for psi goes from 0 to 1. We need to convey all this information to MATLAB. Okay, we need to convey what are the boundary conditions, where are the boundaries located, what are the differential equations. Okay, we need to convey all this. Now we ask the question, is it linear or non-linear? The answer is it is linear as long as k is constant. As long as k is a constant. Now the problem with MATLAB is it cannot solve a second order equation. So you need to convert that into a set of first order equations. Okay? So how do we do that? This is again, you might have seen in differential equations course. If not, try to follow the mathematical development here carefully. It's not very difficult, but our task is to first recognize that a higher order differential equation can be represented as an equivalent system of first order equations. Okay? So here I have a second order equation. We can write this. MATLAB cannot solve this. Okay? So in order to use MATLAB, we need to rearrange this into two first order equations, a system of two first order equations that is representing the second order equation. And that's a very straightforward recipe. Okay? It's a recipe that you can blindly apply and always be able to convert that. What is the recipe? You first recognize that I have the highest order is second order. So I'm going to have two first order equations. So the number of first order equations is the same as the highest order of the original differential equation. So in this case it's second order, so I'm going to have two first order equations. So you define two variables. The first variable is y1, simply theta. that is the dependent variable that comes to the original one, I'm going to call it as y1. Now I need to represent these unknowns in terms of a vector because I'm going to have more than one first order equation. Okay. Then I take the derivative of that unknown, d theta d psi, and define it as my second function. So I have two functions, y1 and y2. y1 is going to be the same as theta, but y1 is going to be a function of psi because theta is a function of psi. Okay? And y2 is the derivative, d theta d psi, but y2 is also going to be a function of psi. So I'm going to have two equations, but the highest order derivative in both the equations will be only one. When I formulate it like that as a system of first order equations, MATLAB can handle that. In the next class, we will see how to set up in MATLAB and solve it, but we want to complete this process of representing it as a system of first order equations. So the first step is always a blind step. Define new variables y1 and y2, and these are simply y1 is the function, y2 is its derivative. If I have a third order equation, what will happen? I will define y1, y2, y3. y1 will be the function, y2 will be the first derivative, y3 will be the second derivative. Okay, that's a recipe, the part of the recipe, the first part of the recipe. Then what I need to do is I need to write this as a system of first order equations. That means I need to write dy1 d psi equals some function f1, dy2 d psi equals some function f2. What are these functions? I need to fix these functions in such a way that the original equation is captured in that representation. Then I can pass to MATLAB what is f1 and f2. MATLAB can integrate f1 and f2 just the same way it did for ODEs of initial value type. Okay, so you need to just convert that into a vector form of equation and then transfer it into MATLAB. So our task now is to find out what these functions are, f1 and f2, such that this system becomes equivalent to that system that you have, the second order system. Okay, so from the first equation, from the first definition, y1 equal to theta, I take its derivative. So on the left hand side I get dy1 d psi, and that is equal to my first function. Okay, but y1 is defined to be what? y1 is defined to be theta, so when I take the derivative with respect to y1, I need to take the derivative with respect to theta. So dy1 d psi is the same as d theta d psi, but d theta d psi is nothing but y2 from the second definition, from this equation. Okay, so the first equation is dy1 d psi is equal to y2. That's the first equation. Okay, so this here becomes is equal to y2. So we have found out what is the first differential equation. dy1 d psi is equal to y2. Any question? This is heavy math, I guess. How many of you are finding it? Are you following so far? I think it's just a lack of attention after 15 minutes. Right? And enough of math for them. If you don't ask me questions, I get edgy because I feel that I'm not getting to you. Okay? So, the next equation is dy2 d psi equals f2. But in order to get that, what I'm going to do is, I have the second definition for the variable y2. I take its derivative, dy2 d psi. Okay, I take its derivative dy2 d psi, and whatever that is, I'm going to call that as f2. And I want to find out what f2 is. I've already found out what f1 is. f1 is simply y2. Okay, but what is f2? f2 by definition, dy2 d psi, is the second derivative, d squared theta d psi squared. Okay, but what is d squared theta d psi squared from the original equation? D squared theta d psi squared, if you move this to the right hand side, is the same as m theta. So what is the same as? What is m? So what is theta? Theta is y1. So m times y1. So we have found out the second equation f2, and f2 is equal to m times y1. So you have two equations and two unknowns. The two unknowns are y1 and y2. The two equations are dy1 d psi equals y2, dy2 d psi equals m times y1. Are they coupled or not? They are coupled. Why? Because y1 is affected by y2 and y2 is affected by y1. Okay? But these are two first order equations. They are exactly the same as the original second order equation. How do you show that? If I ask you to take a moment and show how these two first order equations are the same as the second order equation, what will you do?
How to show that the two second order, make this question, the two first order ones are the same as the second order.
That's what I'm saying. And what I'm saying is I have converted the second order equation into an equivalent system of two first order equations. So this path you can always go through. Okay, if I give you a higher order equation by defining enough variables, the same number of variables as the highest order, you can follow this procedure. In the next assignment, I will give you an example for you to work on. Okay. But my question now is, I'm asking, if I give you a system of first order equations, can you produce the second order equation? What I showed you is, if I give you a second order equation, you can produce a system of first order equations that is identical representation. But how would I go back? Get rid of the variables. That's elimination. Here we are creating variables. Right? We have created y1 and y2. So you can substitute and eliminate y1. And represent it in terms of, eliminate y2 and represent it in terms of y1. Okay, so you should be able to reverse the process.
How many variables do we need in order to convert a second order differential equation into a first order differential equation?
So the number of independent first order equations you have will match the highest order. So if I give you three first order equations and say eliminate two variables from that to produce a third order equation, you should be able to do that. Okay? So, we are now forgetting, we started with temperature and x, we transformed that into theta and psi using dimensional analysis, and then we are saying, okay, I'm going to forget about theta and psi, well, psi is still going to be there, but I'm going to introduce it, the problem in terms of y1 and y2. So I'm going to solve for y1 and y2 as a function of psi, y1 and y2 as a function of psi. But remember, y1 is the same as theta. So if I solve for y1, I know theta. If I know theta, by using the definition of dimensionless numbers, I could find out what t is. T as a function of x. So I need to be able to transfer the boundary condition also. The boundary conditions were written in terms of theta at psi equal to 0 and theta at psi equal to 1. Now I don't have theta. I've forgotten theta. I've converted that into y1 and y2. So I need to express the boundary conditions also in terms of y1 and y2. How do I do that? Well, y1 is nothing but theta. So if theta at psi equal to 1, what is y1? Y1 is 1. But what is y2? At psi equal to 0. I don't know. It won't be 0, it won't be 1. I don't know what it is. But I don't need to know. Because all I need is two conditions. If I have two first order equations, I need two conditions. Keep this picture in mind. This picture tells you that the temperature here is 1, but its gradient is y2. What is y2? Y2 is the derivative of theta with respect to psi. I don't know what the derivative is. It's going to come out as part of the solution. I don't know what it is, but I don't need it. Then I look at the second one, which says that theta at psi equal to 1 is 0. But theta is y1, so y1 at psi equal to 1, that is at the tip of the pen, is 0. So I have two conditions, I have two first order equations, I'm ready to do now in MATLAB. Program this in MATLAB. Yeah?
Why do you need to define y1? Could you just define y2? I don't understand why you need to define y1. Can you just say just theta?
Yes. You can certainly do that. You can define a vector y. In the first element you have theta, and the second element you have y2. That's what you're saying. That's fine. That's entirely, yeah. That's entirely. I just wanted to transfer the symbols in a consistent vector form, because when you go into MATLAB, you will have a vector y. The first position of the vector will represent theta. The second position will represent d theta d psi. That's all you need to know. Yeah. Now I have this think, pair, share exercise for you guys. Write these two equations in vector form. Take 2 minutes and see whether you can put them in vector form. What do I mean by vector form? I must have an equation like this, dy, d psi, equals f of psi. So y is a vector. Y is a vector which consists of y1 and y2, or as he pointed out, theta and y2. And f is a function which consists of f1 and f2. So what are these two vectors? What is the vector y and what is the vector f? Just take a few minutes, talk to each other if you like, and come up with that vector representation.
You kind of a strange question, but exactly what equations do you want us to turn into a vector?
I have these two equations, dy1 d psi equals y2 and dy2 d psi equals m times y1, and I have these two initial conditions. I want them to be transferred into one equation in vector form.
Okay.
And the vectors are y vector consists of these two elements, theta and y2 or y1 and y2. In fact, that is trivial. So the real challenge is what are the elements in the vector function f on the right hand side. That's what you need to understand. It's not a very difficult exercise. It's a trivial exercise if you followed everything that we have done. So it's a kind of a check. So on the left hand side, I will simply have dy, d psi. Y is now a vector. I'm putting an underscore there. That has two elements. Okay. On the right hand side, I have a function which is a vector that has two elements. What are those two elements? Any ideas?
Y2 and my1.
Y2 and
My1.
my1.
Two by two.
It's a vector, two elements. So two rows and one column, 2 by 1. And
When you write it 0, 1, m0 times y1, y2, can you write it that like that we did in the previous? It says 2 by 2.
yeah, you can write it as a vector matrix form if you want. Yeah. So here I'm saying write it in as a vector function, but you can also write it as what you're saying is 0 and 1 and m and 0 multiplied by y1, y2. That is also fine. Now for linear problems, you will be able to do this part. But if the problem is non-linear, you will not be able to do the right-hand side part. You can write it only like this.
Oh, okay.
Those are only two functions. Now, let me ask you, how many of you, maybe am I beating this to death? You guys are familiar with it? Because when I get an answer like that, I say, oh, maybe I'm wasting my time. Okay. But how many of you have difficulty in this? Now that it is revealed, we understand what I was expecting. It's a very simple thing. Arrange the two functions. The first function we get y2, and the second one we get my1. So y2 goes into the top, my1 goes into the bottom. So I'm saying this is a vector representation. Vector has many elements on the left hand side, many elements on the right hand side. We take the corresponding elements from the left hand side, equate it to the right hand side, and should get those component form of the equations. Okay? So these two are the component form of the equation, and this is the vector form of the equation. Just one line. But what you need to do, the purpose of all this exercise is, you need to tell MATLAB, these are my functions. So we are going to write a MATLAB function which takes y1 and y2 as an input and returns f1 and f2, the two functions. And that is why all this exercise is for preparing that. So this is your f1, this is your f2. These two vectors will be returned by the function that you are going to write. Any questions? Okay. We need to get into MATLAB, but I think we don't have time for MATLAB today. But I don't want to let you guys go. Hold on. You still have 5 minutes. So let me give you an example, another example. and ask you to do this exercise. Okay, so I have 10 d cubed y or d cubed theta d psi cubed plus 5 d squared theta d psi squared plus 3 d theta d psi plus theta equal to 0. Let me make the theta squared equal to 0. Okay, and I have boundary condition theta at psi equal to 0 is 1, theta at psi equal to 1 is 0. Now this is a third order equation. Okay, so I need three conditions. So I'm going to give you another condition, which is d theta d psi at psi equal to 0 is 0. My question is, if you have understood this lecture, I say at this stage, go and convert that into a system of three first order equations. dy d psi equals f of psi. Okay, y now is equal to three elements, y1, y2, y3. And I need you to find f1, f2, f3, such that this system of first order equation is equivalent to those equations and boundary conditions. Okay? So what I would like you to do is do this before next Thursday as an exercise. Okay? And I will come and discuss this on Thursday. And I will let you go 5 minutes ahead. Okay, so think about how you would convert that third order equation with three boundary conditions into a system of three first order equations. That simply means you need to find the function f1, f2, f3. And you need to find the initial condition for the boundary condition for y1, y2, and y3. Okay, so there will be three conditions. So you need to convert from theta into y1, y2, y3, or theta d theta d psi, d square theta d psi square. Okay, so by making you go through that, you understand, and I think it'll gel in your mind. And then you will see how to set that up for that. So maybe we can disperse at that. Okay, all right. Thank you.